Okay, I wanted to not only share, the answer key to the district final review with you, but I also wanted to go over a couple key items. First of all, I need to apologize. For some reason, this first page of my answer key does not show my solutions in very clear ink. So hopefully you can follow this. On this first one, you're just looking at a frequency distribution and identifying how many pieces of the data distribution or frequencies are less than 26.5. And so you can see we have these different classes and the frequencies. The 26.5 would be the larger upper limit for this class boundary, so we'd be adding those lower ones to come up with a total of 34. A number, or letter B here, a gumball machine contains 7 grape flavored balls, 8 cherry flavored, 5 lemon. What is the probability of getting 1 grape, 1 cherry, 1 lemon if each ball is removed and then replaced? This term, then replaced, is really important before choosing the next from the machine. You can't really see my writing very clearly here, but my probability for that first one being a grape would be 7 out of 20. I put it back in, I still have 20 in there. My probability of getting a cherry would be 8 out of 20. Put it back in. Again, my probability for a lemon would be 5 out of 20. You can't really see that very well. And then I was reducing because you don't know if you're going to have this given to you in fraction form or in decimal form. So I was reducing, cross-canceling, and so forth, and came out with 7 over 200, which would divide out to be 0.035. You could just say 7 times 8 times 5 in your numerator, in your denominator 20 times 20 times 20, and then carry out your division without doing all the fraction reduction, and you would come right to your ratio in decimal form. Okay, in part C, coin is tossed 2 times. Find the probability that the third toss is heads, given that the first 2 tosses are both tails. It really doesn't matter what the first 2 are. We're just trying to find the probability of that third toss. And this is really just testing you that you recognize that each toss is a separate event. And so how many sides of our coin have heads on it? It would be just 1. So our probability of that third toss being heads is 1/2. But this term here, given that, filters the sample space so that you know that you're just dealing with that one event. Okay, part D here is really comparing the box plot to the normal distribution, the terminology anyway. If you remember, in a box plot, you have your data distributed in quarters, and so it's breaking up the quarters, and we can see in this particular one, our data in that second quarter is pretty dense. The first and the third quarters are kind of spread out, but that fourth quarter is definitely, the data is definitely spread out. So if I wanted to, I could draw a normal distribution along here, and it would probably look something like this. But we can see that it's right-tailed. It's very skewed to the right, so that is called right skewed or positively skewed. So option B would be our answer there. For part E, given 12 students, 9 of which are females, if 2 students are selected at random without replacement, what is the probability that, this should just say both students are females. So here we don't have the replacement. Up here we had replacement. So this is a different format here. So we have 9 females out of 12. So our ratio, the probability of pulling that first one and getting a female would be 9 out of 12. Without replacement, we're down one in our numerator and down 1 in our denominator. So what's left in the pool there would be 8 out of 11 would be female. So I'd be multiplying those 2 probabilities together, and this time it's, our options are in fraction form, so this reducing and keeping everything in fraction form gets us to 6/11ths, and I guess I didn't even circle that here, so it'd be part A. For F, one normal curve has a mean of 7 and a standard deviation of 5, and a second normal curve has a mean of 8 and a standard deviation of 3. The curve that is more dispersed or spread out is, we need to decide which one. What they're getting at is the coefficient of variation is our measure of dispersion. So we covered this in chapter 3 if you want to go back and check that out. I think it was the last section in chapter 3. And really what you're doing is you're taking the standard deviation divided by the mean to calculate that coefficient of variation, or to get that measure of dispersion. So in each of these cases, the first curve, I'm taking 5 divided by 7, the standard deviation of 5, divided by the mean of 7 to get this 0.714. The second one, I have 3 out of 8 to get 0.375. So I can see that I have more dispersion in that first one. So we'll circle part A there. For this next one, using the normal distribution, find the curve under the area under the curve between z equals 0 and z equals 1.56. We could do this on StatCrunch, or you can do this on the t-table. I'm sorry, not the t-table, the normal distribution. I wonder if I have that somewhere opened up here. There we go. Going back to my formula, or the review here, the two z-scores that I'm looking for, and I'm looking for the area between them, I found the probability less than 1.56 was 0.9406, and the probability less than 0 was 0.50, and I found that by going into our z distribution, and I'm on the positive side. Z of 0 would be this 0.5 here, and the 1.56, I'm sorry, I've gone too far, 1.56 would be all the way over to the 6th column, would be this 0.9406. So that's how I found it from the normal distribution. Or we could go into StatCrunch, and I'm going to go to Stats, Calculators. I can go down to the normal calculator, and I'm going to click between, and I'm going to leave this normal, we're looking at a normal distribution. I'm going to take care of this. I need to, our lower limit is going to be a z of 0. Our upper limit is going to be 1.56. And click compute, and that's the other way that we could get our probability from StatCrunch. So again, what I was doing there is I went to Stats, Calculators, and down to the normal calculator. Anytime I'm looking at z-scores, I'm looking at the normal calculator. And I can use that calculator when I'm just trying to find the probability. On the next one, we're just looking at a curve here and interpreting this. What type of alternative hypothesis is used here? Well, I've got K, it's a left-tailed, I've got shaded in the left-tailed. What I'm testing here is our mu, or possibly our mu, is it less than our critical value of K? Or actually it wouldn't be our critical value. This is what we're testing, K, to see if it's less than that. So basically you just need to recognize that this is a left-tailed alternative hypothesis. Okay, for part I here, a study of tortoises wishes to determine the average weight of a certain subspecies of tortoise. The standard deviation of the population is 70. How many tortoises need to be weighed, in which we weighed to find with 95% confidence and accuracy within 20 pounds. So we're looking for our sample size, because we know that, you know, we don't want to, we want to have a good sample size so that we can be confident, but we don't want to have to measure more than we absolutely need to. So we're going to be using the formula from, actually I'm going to try to find it on our formula page. Oh, there it is. On the side that says hypothesis tests, I believe it's at the very bottom, sample size needed, where E is the maximum error estimate. You've got your formula for means or for proportions here. This problem is looking at means, so I'm using this formula here, but it's on your formula page. I've also written it in here, you just can't see it very well. Z alpha 2, in other words, the alpha divided by 2. That just reiterates that this is a two-tailed, confidence intervals are a two-tailed event. And then this is supposed to be my sigma, my population standard deviation, divided by the error that is given to us. So we're plugging in the 1.96 is our z-score that is associated with 95% confidence. This is 70 for our population, the standard population of the population, standard deviation of the population. And then our error was 20. And when I plug all that in, I get 47.06, but I need to round up. We always round up when we're calculating our sample size. The next one, assume the 95% confidence interval or mean is 23 to 37. These are just two other ways that could be written. we have a hypothesis test where our null hypothesis is that mu is equal to 19. When we're using our confidence interval, I'm looking to see if that what I'm testing for is in the confidence interval, and because it is not, I would reject the null hypothesis. Okay, in this review page, I think K, L, and M are probably the most difficult for us to work on, just because there's 3 different ways to do it. But we have a running coach who wanted to see whether runners run faster after eating spaghetti the night before. 18 runners were chosen randomly for the study. They ran 5-kilometer race after having a normal dinner the night before. Then a week later, reran the same race after having had a spaghetti dinner the night before. The results are shown in this table. And this table is not the usual table that we see. What I want you to see or hear in this is that this is matched pairs. You are going to be, actually I just went ahead and wrote out what we're actually trying to calculate here, what kind of a hypothesis test. We're looking, our null would be that the difference is 0. Our alternative is that it's not 0, that it's different. They've given us all of our information, which leads you to kind of think that it might be a independent means, two sample independent means that this is definitely matched pair. So you're going to be using this formula here. You'll get that also from your formula page for matched pairs. And we're really only using the data from this last column here. We don't need this stuff here. We don't need to put that in. So you're looking at 15 minus 0, or negative 15 minus 0, over a standard deviation of 6 divided by our sample size. So you'd really need to use that formula, and it comes out to be the negative 10.61. You can also do it on StatCrunch. I'm almost afraid to show you because I'm afraid I'm going to confuse you. But I want to go up here and choose, okay, I've got everything there. I want to go to Stats. We're going to go down to T-Stats, and this is actually a 1 sample with summary. And the reason I'm choosing that is because I really just want to test that last column. I'm going to use the difference, negative 15 is that difference, and the standard deviation is 6. So that's the summary information that I'm going to put in with a sample size of 18. So my mean is negative 15. Sample standard deviation is the 6, and the sample size was 18, and everything is set up other than, everything is by default set to go, and I end up with a negative 10.61 T-stat, which is what they're asking for. Okay, and the next one, a recent travel magazine claims that business travelers spend an average of $52 per day on meals. A sample of 18 business travelers found that they had spent an average of $54 per day with a standard deviation of $4.25. The test statistic for the difference in means is a t. They've calculated the test statistic as being t equal to 2. So we want to use a 0.01. What does the study find? So you could go to the t distribution and look for, I feel like I'm hiding half the problem here, looking for degrees of freedom of 17, see where that intersects with an alpha of 0.01 to find your critical value of 2.82. And I can do that here. I've got, totally forgot what my sample size was, 18. Okay, so 18, and so our degree of freedom was 17, and we're going to go over here to 0.01 would be that 2.898. So that is our critical value. So when I go back to the formula here, we were told that our test statistic came out to be 2.0. So they've done the calculating for us. We just had to find this on the t distribution. So we can see that that is smaller. This t, the test statistic of 2.0, is smaller than our critical value. So if you're doing that, I think my mind wants to think of the critical value method. I can see that that is to the left. It would not be in the tail, so we would not reject the null hypothesis. But basically this t-stat of 2.0 is less than that critical value, so the test statistic is low and we would not reject. You could go into StatCrunch and do t-stats Again, I'm afraid almost to do this because I don't want to confuse anybody. You could go into stats. We're going to go down to T-stats, and we could do one sample with summary, and we could put all of our information in here of 52 is what, no, actually our sample mean from our sample was 54. The standard deviation was 4.25, and our sample size was 18. And again, our default is set for us. Nope, it's not. We have to say that the mu is equal to 52, because that is what the travel magazine is claiming, that it's equal to 52. And so we're going in here, we find that we have a test statistic that is 1.99, pretty close to the 2, but our p-value is high, much higher than a 0.01. So again, that would say we would not reject the null hypothesis, but that was different reasoning, using the p-value rather than the test statistic. Part M, looking at this one, a landscaper wants to see if his customers have a preference in the color of flower purchased. His data is shown below. The test value of chi-squared is the data, the chi-squared test value data for this data is 9.95 at alpha 0.05. So the fact that we're using the chi-square, you should be thinking about standard deviation or goodness of fit. So we have really 75 different, actually it doesn't really matter how many different preferences we have from different customers. It's the fact that we have 5 different categories, so we have a degree of freedom of 4. We could look at the chi-square distribution for degree of freedom of 4, and we're using alpha of 5. So if you're using that, I'm looking at 4 all the way over here to 5 would be 9.488. So going back here, that's how I found that critical value. But I'm comparing this 9.95. That 9.95 is greater than this 9.448. It's to the right of it. That would put it in the rejection zone. So there is enough evidence to suggest that customers have a preference for the color of flowers, so we could reject the null hypothesis, which would have been that there is no preference. Another way that you could do that to find that critical value, again, I'm afraid I'm going to confuse you, but I'm going to go into chi-square, or into StatCrunch, and I'm going to go to stats, calculators, and I could do the chi-square calculator, and again, I'm kind of looking for I've got a degree of freedom of 4, and I don't know what the test statistic would be for that, but I could put in, I want to evaluate this at 0.05, alpha 0.05, and I come up with a test statistic. Oops, I put this in the wrong direction. That's what happens when you don't clear things out, sorry. So this would be 0.05. Now I've got everything in there correctly. And so I get this 9.4878. So I can see that that is our critical value that we're comparing this 9.95 to. The 9.95 would be right in here, a little bit greater than that, the borderline critical value that we found here. Okay. Here we have office workers were asked how long it took them to travel to work one morning. This is their stem and leaf plot. If you kind of think of this as kind of a distribution that's propped up on its edge, if you looked at pulling this 2, 3, 4, 5 down along a vertical axis, kind of rolling this over on this edge, you'd see that it gets lower. It starts out small, gets higher, but it doesn't really ever come back down. So that would really say that it is a left tail distribution, a negative distribution, skewed to the negative or to the left side. And anytime we have that, it's skewed either right or left, you know that the mean is pulled toward that tail. So we're asked to, not actually calculate the mean and the median for all of this, but we want to know, what would you expect? Is the mean higher or lower than the median? And we know that the mean is always pulled toward that tail, so we would expect the mean to be lower than the median because this skewing to the left.